Alright, so in today's video, we're going to be talking about types of numbers that you'll see quite often in algebra and number theory. And this is by far not an exhaustive list of number types, but these are definitely some of the more common types you'll see. And so the first value we're going to go into is the real set numbers. And the real set is often denoted as uppercase R, typically with two bars which, uphold this loop, which creates the R, and it's known as the real set. And excuse my handwriting, but that does say real on it. And so you're going to start out with any value, e, pi, 3 halves. A real value is defined as anything that does not contain the value I within it. But it can be anything, such as a whole number, a fractional value, or an otherwise infinitely going number, such as pi or e. These are all types of real values that you'll see in mathematics. And so a more restrictive type of real numbers would have to be the rational numbers, and the rational numbers are typically denoted as uppercase Q. And the rational numbers basically say, okay, if you have two values, a over b, and a and b are both integers, then it's a rational value. So if you have 3 over 5, it's rational. If you have 5 over 3, it's rational. And if you have things like, a over 4 or 6 over 3, which come out to whole numbers, it's also rational. What's not rational, however, is when b equals 0, because if b equals 0, then you have something divided by 0, which is not necessarily well defined in mathematics most of the time. And that's why, as long as b is not 0, and a and b are both integers, you'll come out with a rational value per definition. And a rational number can also be put into a more restrictive sense than reals restrict rationals, and that you can have integral values or integers, and the integer is represented most commonly by a z, and it's probably a bit difficult to actually create a good-looking z by hand, but if you see this, then you should know that this is basically just saying it's an integer. And an integer, all that is just a word that means, okay, you have a whole number. So 7, -7, -3, +3. It doesn't matter if they're negative or positive. As long as they are whole numbers, it will come out to be an integer. So if you have a over b, if b divides a evenly so that the remainder is 0, then it's an integer as well. It's just that this kind of notation is kind of, awkward for an integer, because you could immediately just simplify this as a whole value without a denominator other than 1. And a denominator that is 1 doesn't necessarily have to be written out like that. And then finally, if you want to be most specific with these types of values, you're going to have what is known as a natural number, indicated very simply as just n, which stands for natural. And so when you think of naturals, you should think of counting numbers that you count. Especially as a child, you can go 1, 2, 3, 4, etc., right? When you're talking about naturals and you count, you don't necessarily think of negative numbers or fractional numbers or even numbers without things that don't terminate, like e or pi. You don't think of those when you think of naturals. So that's just a way to remember what types of numbers you're dealing with naturals. Just think naturally, you know? And the most debated number when it comes to naturals is 0. I would say 0 in my videos will not necessarily be defining as a natural, because in nature you don't necessarily ever have 0 of anything, because another word for that is having nothing of something. And so for my intents, I'm going to exclude 0 from the list of naturals, but everything else, 1, 2, 3, 4, etc., is natural. After you have your naturals and your reals and numbers that you can think of in a quantitative sense, right? You can think of e, although it is weird, 2 and then some impossible to calculate fractional part of the third whole value. And you can have fractions, 3 halves. You can have even, negatives of some things, like debt. Debt's pretty common when you're talking about negatives. But in the real world sense, you very rarely actually ever come across these values. First one being imaginary. And these values take on the form of a times I. Now, a has to be real. You can usually denote something being as one of these terms either with an arrow like this, or you can maybe bracket it like that, or you can just say a is real, either written out like this or in like fully written form. So a has to be real when you're talking about imaginary forms of a times I, and a cannot be 0 in any case whatsoever. When you talk about something not being equal to something, you usually put an equal sign and just cross it out. So this is saying a is real but not 0, and so it's not 0 because if a was 0, then you just multiply the value of I, which is the square root of negative 1, by 0, and you just end up with 0 anyway. It doesn't matter if it's imaginary or not, that rule of multiplying by 0 still applies. And so types of imaginary numbers, you can quite simply put, 5i, 2i, ei, and pi I, or even things like negative 7i. These two, by the way, come pretty useful in some forms of calculus and whatnot. Like, these are more of the advanced forms that you'll see. But you just have to understand that this is just the value of I, square root of negative 1, times the value of e or pi. It's not necessarily that hard to comprehend once you just understand that. But sometimes when you deal with imaginary numbers, you'll deal with this other form called the complex numbers. And complex numbers deal with imaginary numbers, such as a times I, but then they add a real part to it plus b. This b value is real, a is real, so when you write that out, you say a comma b is real. But a, b do not equal 0 either. Because if b is 0, then, well, ai is just either imaginary or real, depending on what a is. But if a is 0, then you have a real value b. But if b is 0 and a is real, then you're just stuck with an imaginary unit. So it's important that both of these do not take the form of 0. But anything where they are real, this applies, this complex value applies. So you can have things like 2i plus 4, or maybe e times I plus pi. Don't get tripped up because these are real, these are both complex values. Complex, yeah. And so when you're talking about all of these combined, you'll generally want to organize it as a hierarchy. And so real is the most basic form of any value that isn't imaginary. So you're going to want to start with your huge web diagram that deals with real values, so R. And within that, you're going to want to put in a section where they are, rational, you see. Because not every real value is rational, but every rational value is real by definition of rational values. And so after that, you want to put in your integral values in the middle like this. So your integral value comes in the form of z, and it's important that you make the value or circle of z smaller than that of q, because not every rational value is necessarily an integer, because you can have fractions that don't reduce to a whole number, but you will always have whole values for integers. So you're basically saying that every integer is rational, but not every rational value is an integer per se. And then finally, you come out on top with your natural numbers in the middle, the most specific form of real numbers, you see. And then here, in the outer skirts of this bubble, you want to put in your imaginary values, your imaginary I. And it's important here that you leave a little bit of shading or a little bit of area here, because this includes when a equals 0. It's not conventional to say that a is 0, because then you're just stuck with 0. But technically, 0 times I is in an imaginary form, but it's also a real value once you equate it all out. So you have to leave a tiny bit of room for that. And then finally, you're going to put your complex value within this awkward intersection here, your complex. Because, again, A and B can be 0, and it's still technically in the notation or form of a complex value. It's just that it just comes out to 0, or otherwise real value. So you have to make sure they take into account this small intersection that really is negligible when you think about all the possible combinations of complex and imaginary. And in fact, some Venn diagrams actually just have them, outside of the entire real spectrum entirely. And both of these are correct in technical terms. It's just that for all intents and purposes, I'm going to use this as my reference for future videos. So if you see a diagram of either this or this, understand that it is correct, and it should not trip you up that you see a different form of the same web. And so that's going to be all for now, and I hope to see you later. Have a good day.